All right. Hello, everyone. Thank you for coming to this talk. Today, we are lucky to have Professor Méndez, who's a planetary astrobiologist and director of the Planetary Habitability Laboratory at the University of Puerto Rico. His research focuses on the habitability of Earth, the solar system, extrasolar planets, and you have plenty of research experience at NASA Goddard and other observatories. So I'll hand over to you. Take it away.
Thank you for having me. Thank you for the invitation. I will be sharing my screen, I think, now.
Yes, we can.
Okay, perfect. So I am Professor Abel Méndez from the Planetary Habitability Laboratory. Thank you for the introduction, or PHL for short, at the University of Puerto Rico. We'll be talking about our research work, our lab, and the Arecibo Observatory. So what I do is mostly in the field of astrobiology. Astrobiology is the study of life in the universe, including life on Earth. It can be divided in the study of the origin, evolution, distribution, and even the destiny or future of life. People tend to think that astrobiology is just searching for life elsewhere. But actually, it starts by looking at our life on Earth and in the context of the rest of the universe. For example, our planet was formed and the first conditions necessary for life were established in our planet. So that's biology plus astronomy and planetary science. How life evolved in our planet, including some astronomical events that touch life on Earth, like impacts from meteorites. So that's, again, astronomy and biology, how it distributes, the land masses are moving, climate is changing. So that's also planetary science and biology. And our future of life, are we gonna stay here on Earth? Are we moving elsewhere? So that's, again, biology and astronomy. So you can do astrobiology just thinking about life on Earth, and extraterrestrial life is not necessary. In my talk for today, I will talk more in the other part. What about extraterrestrial life? What we can learn about extraterrestrial life, and how that's related to astrobiology. Well, here are area photos to scales of our lab at the University of Puerto Rico, Arecibo. Arecibo is a town in Puerto Rico. It has the name of an Indian king of sort from long ago in Puerto Rico. And our lab is this town at the University of Puerto Rico. And here is a picture to scale, and you can see a field track here, but also you can see a picture of observatory to scale. So the size of the dish here, this is an old photo, of course, is 300 meters. The Arecibo Observatory is famous because many things, and one of the things is the Arecibo message, which was sent in 1974. A month like this month in November, toward the Hercules star cluster M13, which it would take about 22,000 light years. So it was an exercise of and a show off of the capabilities of the observatory, which was upgraded at that time. So they pick a star system during the daytime, so they can send this radio signal as a test of the capability of the observatory. And And that was amazing. And the message here, and here is the encoded message. But you can also see here what it means: numbers, chemical elements necessary for life, chemical compounds necessary for the DNA, and then the structure on the DNA, then the humans and the population back then of humans, and then our planetary system highlighted. So so it's shown that human comes from the third planet, and a plan of the size of the observatory, which was used to send the message. So this was a test of the, as I said, of the observatory. So it's not something that we're expecting an answer back. But Arecibo has been doing also, or have done before, the actual search for extraterrestrial intelligence signals from space. And that was because of Project Phoenix. From 1995 to 2004, Project Phoenix used different telescopes. That's this institute used a different telescope around the world, Park Observatory in Australia, a Green Bank in the US, and the Arecibo Observatory, which was the last one. So it was until 2004, that was the last time the Arecibo Observatory was actually used for active search of extraterrestrial life. Since then, there have been running many other projects, but none related, at least directly, with the search for extraterrestrial intelligent life from radio. What science at Arecibo is being done? So Arecibo do 3 fields of science. You do atmospheric science, planetary science, and astronomy science. Science, but not many people know that it does planetary science or even atmospheric science. And it's being used to study our atmosphere, especially the ionosphere. And in terms of the planetary science, is used to create maps. And Arecibo Observatory was the first to create the first map of Venus in the early 1980s. We didn't know back then what was the surface like of Venus. So Arecibo Observatory was the first one. Later on, a spaceship with radar capabilities, we were able to measure the surface topography of Venus. But Arecibo was the first one. And here is the actual map that they made in those days. But it has been used mostly for tracking asteroids after they are being discovered, just to learn their properties, their size, speed, to improve their orbit predictions and their physical properties. And these 2 areas, atmospheric science and planetary science, need something else from a radio telescope. Also the capability to be a radar. So most radio telescopes are only just listening to any natural radio emission from the universe. But Arecibo also have the capability of being a radar. So it was able to transmit. So that was in 1974, the Arecibo message. For example, the biggest radio telescope right now in China, the FAST telescope, is only a passive radio receiver. It's not capable of transmitting. So Arecibo was still, until its collapse, the largest radar in our planet. So with 300 meters. The next big thing is 100 meters, and it's in the US with radar capability. So we lost something big, one capability, because that it was very important for planetary protection. To once you detect something that could be one asteroid that you might think, based on the initial calculation of their orbit, that it may be hard, it might have an impact probability in the future. Then Arecibo was used to verify that and calculate, make precise observation of their orbits, and especially their size and shape. Unfortunately, when we have in 2017 Oumuamua, the famous interstellar asteroid, and you have been seeing the media that some people even think that it might be some artificial remaining or artifact from an alien civilization traveling through the solar system. But the consensus is it was just a not so common asteroid, just reaching our solar system. But there's still doubts, especially about its shape. And unfortunately, in 2017, in October, when this object was discovered, the Arecibo Observatory, the only instrument in our planet that had the capability to get a better shape, because it's using radar of similar object, was not available because we had Hurricane Maria in September, just 1 month before. So the Arecibo Observatory was not operational. It was not operational only after 5 or 6 months later on. And by that time, this Oumuamua was very far away. It's true that Oumuamua was small and within the limit of detection anyway, if the Arecibo Observatory was, but it probably will give us something else that about this object, but we missed that opportunity. And of course, being a big radio telescope, the Arecibo Observatory does a lot of astronomy and radio astronomy science, star galaxies, and the universe. So those are the three areas that Arecibo, and you have different groups working in these areas. But our lab, which is at the university, so 30 minutes driving from the observatory, we do more research related to astrobiology, as I said. We do that's understanding the habitability of any planetary environment. We also focus on terrestrial habitability, solar system. I mean, that means the planet like Mars and moons of Jupiter, like Europa. We also do a lot of work with exoplanets and habitability, and our work with the radio astronomy. Some of this work with the radio astronomy and the Arecibo Observatory is related to habitability, but some of the work is just pure astrophysical. And we also have a few projects related to archaeoastronomy also. So the two main projects that we work with in our laboratory are the Visible Paleo-Earth. This is a photorealistic reconstruction of Earth in the last 750 million years. We have enough paleogeography data until that time to create this rough how Earth looked like. So we added combining what we know of Earth today in the colors of the vegetation, because we knew back then where was the forest, where were the ice area. So we just reconstruct more visually photorealistic representation of what Earth looked in this event. And we use in this project not only as an educational project, but also as a scientific project to understand, because of different positions of our land masses, and depending on the inclination of Earth rotation, which was different back then, we are trying to reconstruct the surface temperature expected from this configuration and compare those surface temperature with the actual measurement based on thermal proxies, and just to see how they match. and to understand what was the impact of the distribution of land areas of our path toward the temperature, the global temperature of our planet. One of the most popular projects is the Habitable Exoplanets Catalog. This is a catalog of potentially habitable exoplanets or planets around the sun that have been discovered roughly since 2010, so 10 years ago or 11 years ago. So, and actually this December 5th is the 10-year anniversary of this catalog. We created this catalog to keep track of those exoplanets that might be considered potentially habitable, that have been detected by different observatories and different techniques everywhere. And what we do is based on their size, if they have the similar size, and if they have a similar orbit as Earth, which it also depends on the star type, then we can say that it has a chance for having if they have an atmosphere, they have a chance to have liquid water at the surface. So all these, here you see Earth in the picture, Mars, Neptune, and Jupiter for scale. And you see here the 24 most similar to Earth in terms of size, temperatures. These all are artistic representations. We don't even see these planets by telescope, even as a dot. So we don't have any idea on how much atmosphere is any, how much water they have, what are the surface features. So the only correct thing here in this visualization is about their size compared to Earth, and that we know that they have a good orbit, or they orbit in what we say the habitable zone, or the stellar habitable zone, the region around the star, that they may have a condition, having atmosphere similar to Earth, the right condition for having liquid sulfur water at the surface. So, and I said that we don't even have a picture as a dot of this object because most exoplanets are detected not because we see them directly, but we see them indirectly on how they perturb the star. Maybe they block part of the star light when they cross in front. That is the transit method. Maybe they tug the star, and we can see this motion in the tug. So by different ways, there's astrometry and radio velocity method. Just see the star moving because the influence of the gravity of the planet. Then we see that the planet is there. So that's how most of these planets are detected, sometimes with one method, sometimes with two methods, which is good to confirm that they are for real there. We have seen indeed pictures individually of this exoplanet as a dot next to the star, but that's because those planets are giant, far away from the star. And usually they are hot because they are young planets. Then we can see them as a literally dot in the sky, in the space next to the star. Otherwise, we have to rely on how they perturb somehow the star just to detect them. And eventually, in this decade and future telescope, especially future telescope, more than this decade, future telescope, we'll be able to see these objects, actually some of these that I'm showing here in this picture, and as an individual dot. And that will be great because still you will see a dot, so no idea about the surface properties. With using a spectroscopy, you will learn something about the atmosphere. But as the planet rotates, it will probably become brighter or dimmer depending if it has land areas or ocean. Land areas are more reflective than ocean areas. So you keep looking at the planet, this bright dot, and you see that it changes through time. Then depending on that change, the only explanation could be that it has ocean and land areas instead of dark areas in land, dark or brighter areas. So that's exciting, just to something more that we will learn in the next decades. One of the biggest projects in our lab is our Planet Hab collaboration. This is a collaboration to understand habitability and try to use these habitability models that we are developing to different targets, from terrestrial environments, extreme environments, planetary environments like Mars, Europa, in Jupiter information. We also have a large group of students, and we have a large group of undergraduate students working on our projects. And some are biology students focusing more in terrestrial environments and the terrestrial habitability. And I have also some students working with part of the astronomy too. Here is our latest paper on habitability models for astrobiology, which we published in Astrobiology last August. This paper is the first of many that we will publish soon about how to apply these habitability models to different environments on Earth. And this picture here is me with three of my undergrad students, Kevin Ortiz. He's now a graduate student at Harvard University. And Nicole and Marcos will be soon applying for graduate school. And let me explain more about what we mean about habitability, because it's a strong point on our work. We can divide habitability. First, the definition: habitability is the suitability of an environment for life. We can divide habitability in three parts based on its definition. A suitability, a metric, which means a metric of process for habitability. An environment, which defines the space and time and region together with some variable interests. And a life form of interest at any level, from individual species to world biosphere. This is a common framework to create a habitability model, but the solution is always relative to these three parts: a proxy, an environment, and a particular life. So if you want to model habitability, you need to consider these three parts. For example, habitability based on productivity of forests as a function of temperature and precipitation for primary producers. So you see here that when you are trying to consider the habitability of any environment, you have to pick your environments of interest. Usually people think on habitability is determining if a place is habitable or not, a yes/no answer. And that is a oversimplification and a confusing oversimplification, because if you really want to know if a place is habitable in the common sense, having able to support life or not, you have to find life there or put life there. There's no other way. So when we are considering the term habitability, and this is how is addressed in biology, is how suitable the environment is for life, but as a function and some specific variables. So the problem here is that you have to, all the variables that are affecting in the environment, you study just one or two, trying to address different things. How important is this variable? Is this a limiting variable? Are there more important variables? So you always study habitability by parts, and not try to answer is the environment is habitable or not in the common sense, just how good it is as a gradient of possibilities. We are working on an extension of the habitability models using ecology, where habitability is proportional to the mass and energy available for life. Only a small fraction of the total mass and energy of the system is usable for life. Here in the red box is the differential expression where we can see the habitability H depend on fluxes of mass and energy. Fluxes in terms of space and time of mass and energy. It is always necessary to define a region of interest in space and time. For example, a patch of soil or a volume of water or air or a planetary surface is considering, for example, the habitability of a biosphere. Here in the blue box is a very convenient way to calculate habitability relative to some other known environment and normalize in a scale 0 to 1. So for simplification, these habitability models, one technique is just to normalize relative to some standard environment. The standard doesn't have to be the best environment. It's just a reference environment. So you're measuring habitability relative to something else. And what you need here is to what mass is available for life, which could translate to the concentration of some nutrients. What energy is available for life, that depending on the kind of energy that you're considering light or a chemical energy. A quality factor, this is something that depends on the life form that you are considering, how these organisms react to that mass and energy or other parameters in the environment. And H is our mass energy habitability. So this symbol here, the Earth symbol, is just the reference if you are considering that you're evaluating your habitability based on a reference to a terrestrial environment. We can use the analogy of an electric circuit to understand how to combine many parameters in the equations. Are necessary to subtract, for example, from the gas, liquid, or solid phases are used in parallel, and thus can be mathematically accurate as a resistor in parallel. So no matter how many parameters that you consider, for example, how much carbon is available in the environment, how much water is available in the water, how much oxygen is available in the environment. So you can combine those as and you will have a reduced mass, which usually is proportional to the ingredient that is less available for life or limiting nutrient. And energy will flow through the system, and that's what habitability is. Then the total mass required for life becomes a reduced amount constrained by the limited substrate from available substrates. This expression reduced, if you try to work out this mathematically, this is in terms of growth, to reduce to the classic monod growth equation for one substrate. Applying this, let's go to a specific example. Here we apply the model to all possible temperatures and relative humidity variation on Earth and Mars. So here we are evaluating the habitability of the surface of Mars with respect to just temperature and relative humidity, which is an indicator of how much water is present. And temperature is an indication on how much energy is present. And the spatial region here, this box here, shows the condition necessary for life as we know it. Temperatures over minus 18 degrees Celsius to 55 kelvins is about 0.6, or in terms of relative humidity, that's 60%. So that's most terrestrial life experience these conditions here. And here you see in different plots, we have data here for actual data for from Mars Curiosity, the rovers, Mars Phoenix lander, a simulation of the general global circulation of Mars. And you see here, and this is in red, and here you see in blue for Phoenix, and this is the simulation, global simulations, global circulation model of Mars. And they, from this particular region where we know that most life is can be sustained. Yeah, we also have actual data for the Atacama Desert, which match some of these conditions that we know are good for at least for microbial life, but they are also sometimes way below that, but never as bad as the Mars. And here for a rainforest, a yunque in Puerto Rico, these are light green, which are always almost most of them within these good conditions for life. So what we can conclude here is that rainforests are about 1 order or 10 times more habitable than the Atacama Desert with respect to temperature and humidity alone. Mars, 2 to 3 order of magnitude, that mean 1,000 times less habitable than the Atacama Desert. So you see a big difference here. This is just 10 times, and this is 100 to 1,000 times less. We can see this in more detail. Here are 2 plots, 2 days of Mars, 2 particular days. A hot day, temperatures are hotter, and humidity doesn't go about 20%. And here is a day of Mars, not that hot, but humidity almost go at 80%. And below here, each of these days, temperature and relative humidity is our model habitability calculation for that environment. And we see here the habitability during, and this is about the 24-hour period, which is similar to the terrestrial hour. And you see that under the nighttime, and it's in the morning after 6, when the sun rises, is that the habitability for Mars with respect to temperature and humidity increases. And then by the 15 hours, then is a maximum. It's similar for the also a bit lower for the wet day, the shape. So does this mean that these are the right conditions and the best times to look for trying to detect life? Well, if you see the actual habitability values, and here the standard of comparison is the Atacama Desert. This is way, way, way lower than anything Atacama Desert. As I said before, over 1,000 times less habitable. And this is with respect to temperature and humidity. If you consider other bad things that are happening in the surface of Mars, for example, UV light, this surface also receives more UV radiation. This won't make this any better. So if you calculate that even with just these two variables is bad, or any other thing could stay the same or make it worse, not better. So you see already how bad it is, the surface of Mars compared to anything on Earth. And that's why it's important just to have this model. So we can, so otherwise we'll be saying, well, Mars, this is a polite way to say non-habitable, but we will be saying this place is not habitable, not habitable, not habitable. But now with this model, we will say those that are non-habitable, we could say how bad each one is and compare those that are bad, or even those that are good, if that ever happens. In another topic, exoplanets have been studied by the Arecibo Observatory. And you already know that we do a lot of collaboration with the observatory. And the first planet that were the first ever planet that were detected around other stars were detected from the Arecibo Observatory in 1992, the famous pulsar planets. Everybody remembers the 1995. It was the year that we detected exoplanets. Those are planets around a common star, sun-like stars. But around any type of star, it was the Arecibo Observatory 3 years before that pulsar planets. This was a totally surprise discovery. The team, Boscan and Freyr, were not trying to detect exoplanets. In fact, if you ask back then if they think, or anybody at that time thinking about planets, about pulsar, that's the worst place to look for planets, because pulsar are the remnants of a supernova. When the star goes supernova, it ejects most of the materials from the surface, and it always leaves a compact core that contracts further and becomes a pulsar. That's one way that stars could die. There are many other ways. They could become a white dwarf that would apply for our sun. If they are big, they can end up as a black hole if the star doesn't get destroyed, depending on the supernova type. But so you have this pulsar planet. They are actually neutron stars. And depending on orientation, when they spin and emit these radio emissions, if we can see these radio emissions from Earth, we call those pulsars. And they will, and because these are definitely the worst place to look for planets, because those are exploded. So there is almost no chance for any planet there, even if they are far away from the star, to survive this process. So we think that the first detection is a pulsar. So why is that? Is that probably this planet formed after the supernova explosion, when the remaining material condensed, then these are new planets formed after the supernova. We think they're actually right now happening. Even so, we look at many other pulsars, and there are 2 or 3 more known pulsars with planets. So they are rare. So it's even not common for them to form afterward. And most of the planets that we have detected is at a more typical sun-like stars. Arecibo was also part of the first detection of brown dwarfs by radio emissions. Brown dwarfs are a type of object between stars and planets, and they emit aurora radio emissions about the same in frequencies that can be detectable by the Arecibo Observatory. And they have been seen from the observatory. And in terms of habitable planets, we are the ones working on this with Arecibo. We cannot see planets, but we are looking at a star with planet, and we're looking at how active are their star, what's the space environment that these planets have to endure due to the activity of the star, because some stars are very quiet and stable like our sun, but other stars are very active, emitting large dose of radiation through solar flares or coronal mass planets, but we are looking that will be very bad to the planet. And we can study those emissions from the stars, and that give you an idea of what the planet that we know already there by other methods that detected this planet. We can understand how likely are those planets, for at least for the atmosphere or the water that they have to survive. So our specific project with Arecibo is the Arecibo radio emission from dwarf star. We're looking mostly at red dwarf stars, Arecibo Reds, the name of our project. And you can see here a list of the stars that we have been looking for some time now. Barnard star, we know it has a planet, Wolf HD 9575, Ross 128, Procyon, some other stars that not necessarily have planets, but we also look at them. But Lytton star and Tigard star. And the star here in Barnard, Ross, Lytton, and Tigard is because we have a lot of observations of those stars. At least Ross 128, Lytton, and Tigard have a potentially habitable planet. So we have been focusing in these stars because we want to understand, as I said, the space environment that these stars are experiencing because of the activity of the star. We have 3 students working in this project. Kevin Ortiz from UPR Rio Piedra, but now he's at Harvard University doing his graduate student. Doing his graduate studies in research related to exoplanets. And Genesis and Ariana are right now here working with data from the observatory. They're continuing working with data at the observatory. And so how come this is possible? Because they are using archive data. And one thing that we plan in next year or so is to explore from our data and trying to search those actual SETI, something that we haven't tried before. We are getting a lot of data from these stars at different frequency bands. And one project here one idea is to look in this data for any intentional radio transmission. We don't think that is very likely, but at least we will know that nobody is transmitting from those stars. And we can constrain that there is no radio transmission from those objects. And that will be something interesting anyway. We all know that the Arecibo Observatory telescope, and I have to emphasize that what it collapsed was the telescope of the Arecibo Observatory collapsed last December 1st, 2020. So this next December is the first anniversary of that collapse. What happened here, and here's the picture of before, is that this tower here, cable, just snapped, and you probably have seen the videos. And these receivers here which include all the important instruments to detect and transmit, because it also is able to transmit. Just slide two back here along this red line, or back to the side of one of the mountains here, and just scratch and go here. After you see the crash here of the antenna and the damage done to the dish, and here in the right side top is the visitor centers. Below here is the control room, but up here in the hill next to one of the towers is the visitor centers. And though the visitor center indeed received minor damage by one of the cables falling, but that was it. All the buildings are intact. So we just lost the big and famous telescope as part of the Arecibo Observatory complex. But what will happen? Well, this dish is now, everything now is cleaned up. 70% of the dish is functional and is left there if, for example, if we want to rebuild it. The three towers that the top of all the three towers broke away about 20 to 30 feet. Then the towers are still there and can still be used if we want to hang another instrument there. So that was clean, made safe, and it was left there for any potential use in the future. Meanwhile, short term, there are other instruments that we'll put in around the observatory. Actually, there are other instruments, even a small radio telescope is not here in the picture, but other instruments might be made operational in the near future here around. While we think what we're gonna do with this, with the main telescope, probably one option is that reconstruct the observatory. So put back toward the dish, which is not a big deal. And instead of hanging the transmitters and the heavy things at the top, maybe put it at the center. And then within the towers or a crane, we can put just a reflector, which will be lightweight. Will be something lightweight, just a secondary reflector. So radio wave will reflect from the main dish, reflect at the top from a secondary dish, and then to the center where there will be the heavy instruments. So this is one option. But the most interesting option, which probably will take 10 to 15 years if it happens, is that something that we proposed last January, the next generation Arecibo telescope, NGAT. So instead of being a single dish, it will be an array of dishes of different sizes. It will be about the same area, but they will put instead on a plate at the same level, but at the bottom of the cavity there. And this plate will move a little bit just to allow for different angles. But the combination of this can also be able to get signals from different angles. So this is what we call a phase array telescope. And it will be able to receive, but also to transmit. We don't want to lose that capability. Also to be transmitter as before, and also a receiver. And this will increase this combination will have this a little bit better sensitivity than before, but we also have a better spatial resolution, and it will be a much better instrument, different frequencies or so. That will be something great. This could be an amazing instrument, but this will take some time. maybe 10, 15 years to happen, if it ever happens. Finally, some contribution of our lab to scientific documentaries. Our lab has been consulted for series like the Cosmos, Space-Time Odyssey, and the Human Universe. Also, some of our work was filmed by National Geographic for the series One Strange Rock, which is available in Disney right now. And so it shows us using the observatory and actually discussing results of what we do at observatory. And more recently, this week it was announced a new Arecibo movie, a whole movie dedicated to the legacy and the future of the observatory. It has never seen footage of the collapse, of the aftermath, and it shows the human size, besides also the science, the human size after the observatory, and what are the plans for the future of the observatory. So I want to share with you, to end my talk, the trailer of this movie. I will turn off my camera because I think that will make this better. And then hopefully you can hear the audio.
Well, it was in 1959 when they started building the Arecibo Observatory, 63 when they finished building it and it saw first light. But what led up to that time of starting in 1959? Well, the key person here is Bill Gordon. What Bill Gordon said is, hey, if we build a big enough, fine enough, high-quality instrument, we'll be able to use a different return from the ionosphere, incoherent scattering. Something new that hadn't been done before and is not that easy to do. Now you might say, why so big for doing this incoherent scattering? It was the beginning of the space age.
Asteroids are moving in space, not only orbiting around the sun, but they are also rotating.
So with Bennu and OSIRIS-REx and DART mission and this legacy of Arecibo, we had a record number of detections in the last few years. Now what?
La ciencia está llena de misterios y tratamos de buscar soluciones a estas preguntas.
Was there any doubt among scientists about whether this was a good project?
There's a lot of work to be done. What would have happened if we didn't have those radar observations?
So as I see it, there's a lot of mysteries in the universe that we need to solve.
The tool, that is, the physical instrument, but what it left behind will be part of mankind for generations to come.
The movie will be showcased first in Puerto Rico, next December 1st and 2nd because of the anniversary. But probably in 2022 will be streamed for internationally. So thank you very much, and I am open to questions.
Awesome. Thank you very much for that amazing presentation and inspiring video at the end. Yeah, we've got a load of questions. So the first one to start us off is, given that it's about 47 years, I think, to the day since the Arecibo message, where do you see us in the next 47 years? Do you think telescopes like this James Webb Space Telescope will take over telescopes on Earth? And where do you see the technology taking us in these next 50 odd years?
A fascinating question, fascinating problem. Okay. We probably will be, and we're planning that, and that we have been trying to do this step by step, and the technique is constructing bigger and more telescope working together, not isolated. And when you build an array of you don't have to be just one radio telescope or optical telescope in one piece. You can build many pieces and separate it as far as possible. As far as possible, I mean the whole planet, or even around our Earth or in the solar system. So right now we have been doing this with optical and radio telescope through creating these arrays in small scale, not that many telescopes, but around the world. But eventually, I think we will be building so many and launching telescopes to space, in the moon, around the sun, and they will operate as a network. And when you have that, that's like creating a whole telescope as big as the solar system. Even that is just pieces of telescope everywhere. And everything will change. That means that you will be able to see, for example, our near star, Proxima Centauri, which has a potentially habitable planet, which we know only because the talk it does in the. With those array of telescope, we'll be able to actually see the planet. Not only the planet, we will look at it as a ball, and you will see surface features. You can go as far as that and tell just visually if it has containing weathers, climate, or even a large civilization spanning the whole continent, constructing a lot. So it will be amazing. So how long this will take? Wow. 20 years minimum, the first huge space network of telescope, then probably 50 years, 60 years. Still within the lifetime of many people watching this program.
Yeah, and you mentioned having like networks of telescopes. With COP26 and all of the kind of environmental things that have come to light recently, what do you think as scientists we can be doing to protect our space, both from space and on Earth?
Well, when you study astrobiology, you're thinking about everything outside our planet if you're interested in extraterrestrial life. But and you probably start thinking naive in this process, because if life is here, then it should be everywhere else. Why we should be unique? But once you understand more about astrobiology, you start to appreciate more how difficult it is for a planet to stay stable enough and long enough to have simple life, complex life like plant and animal, or even intelligent life. So you realize how amazing is our life in this planet and that we are here. You start to appreciate more. So that definitely changed my perspective. So now, even that I'm doing astrobiology, I don't care that much about extraterrestrial life. I just care more about our life. If we ever find an intelligent species elsewhere, my questions won't be about them. But my question will be about, do you know our origins?
It's 3:00.
Do you know anything that might affect us in the future? I don't care about them. I just care about our planet. We know that the life, even if there's a lot of life elsewhere, is far away. And we have to be more appreciate our planet on all levels. And I think that's changed your perspective. And that's, I think, the first step to moving forward to making more scientists aware of the importance of our planet and take care our planet in different ways.
Sure. Yeah, that's really interesting. And we have time for maybe one or two more questions, if that's okay. So you're talking about life, obviously, and as an astrobiologist, it's quite an important aspect. So we've had a question here. Tardigrades have purportedly already made it to the moon. Do you think they're a suitable organism for studying moon habitability, or is there like other models that you could use?
Well, tardigrades are animals that are very resistant to harsh environments, hard doses of radiations, UV, even the space environment for some time. Microbial life is better. Some microorganisms are better to actually living in extreme conditions, better than the tardigrades. The thing is that the tardigrade as a complex thing is an animal, it's not a bacteria. So it is amazing. But still, once you put tardigrades in an environment quite different, it will just survive the environment. It won't thrive in those environments, in those extreme environments. So that probably will be if we travel to planets, like creating habitats in the moon, or especially Mars, our problem will be cross-contamination. Well, or cross-contamination with microbial life, because we cannot sterilize ourselves. We always carry bacteria. We will carry water also from Earth, and then they will carry any organisms, even probably tardigrades. And those tardigrades can withstand for a long time in those environments. So I think that we have to be very careful when we explore our universe, because if those thinking about detecting life elsewhere, and this applies mostly to Mars, have to be careful that those missions are clean enough so we cannot detect ourselves again.
Okay, awesome. So to wrap up, I think we've just got one last question, which is, from your career, do you have any tips for budding young astrobiologists, maybe who are studying life sciences field now, or something like engineering? What would be your main tip for us?
Well, if you want to study astrobiology, you can study anything. There, I have a sample from my own students and other students that study biology and then became astrobiologists. Well, it's in the name, the astrobiology, but astronomy, engineers, mathematicians, and even people that study something else, like music, history, and then later on decide, oh yes, I want to go into science. So you can do your bachelor degree in any area, but if you at some point during that bachelor, you decide, I want to do astrobiology, just go for it. You can study astrobiology now in any university, because most of universities have at least one person or a group doing some astrobiology. So you just have to pick what within astrobiology is your main interest and see in the universities that you want to go, or what university have those things, and just apply to them. So it will be graduate school that will make you an astrobiology. You can actually get a degree also in astrobiology. You don't have to get a degree, a PhD in astrobiology. That's something rare. But you can actually get a degree, for example, from University of Washington. They have a degree in astrobiology. It's a dual degree. You get a degree in PhD in biology plus a degree in astrobiology, if you are into biology. If you are into astronomy, then a PhD in astronomy plus the degree in astrobiology. So you just have to take the courses from the different area that is not yours, just to complete your general training in astrobiology. But you have to realize those are new or relatively new PhD, and most the people doing astrobiology today don't have that degree. They have degree in something else, and then just doing research on astrobiology. So it's easy, it's fun, and to do astrobiology, you can do experimental work, field work, And I mean exploring terrestrial environments on Earth that are related to astrobiology, or theoretical work like we mostly do in our lab.
Okay, well, thank you very much. That was definitely an insightful talk and great to ask you some questions at the end. I believe we can find you on Twitter. You're very active there if you want to find out more. So yeah, that's the end of the session. Thank you for coming, and I hope you have a good evening.
So thank you.